All right, so now we're going to learn how to write thermochemical equations. So chemists use thermochemical equations to represent changes in both matter and energy. And so a thermochemical equation is very similar to what you're used to seeing, except that you have some sort of an enthalpy change to the right of the chemical equation. So here's an example where you have hydrogen gas and oxygen gas yielding water, and you have a delta H, or a change in enthalpy of negative 286 kilojoules. So the enthalpy value, or delta H value, indicates the amount of heat associated with the reaction as written. So the negative value here indicates that this is an exothermic reaction that gives off 286 kilojoules of energy. So if the direction of a chemical reaction is reversed, the sign of the enthalpy is also reversed. So if the enthalpy is less than 0, it indicates that it's an exothermic reaction. If the change in the enthalpy is greater than 0, that indicates an endothermic reaction has occurred. So here you see the reaction as was written before. It has a negative enthalpy value, so that means it's an exothermic reaction. If we were to write the reaction reversed, notice the sign is reversed here. So when water dissociates to hydrogen and oxygen, you're left with an endothermic reaction that happens. All right, so some conventions for thermochemical equations. If the coefficient of the chemical equation is multiplied by some factor, the enthalpy change must also be multiplied by that same factor. So the enthalpy, or the change in enthalpy, is an extensive property. So it basically means that it matters how much you have. So for example, here we have the equation that we had originally. The enthalpy value is a negative 286 kilojoules. If we were to multiply this chemical reaction by 2, then you would end up having to also multiply the enthalpy value by 2 to yield the enthalpy value, which is twice as much as the original. If you were to divide the chemical reaction by 2, okay, or technically multiply it by a factor of 1/2, you would also multiply the enthalpy value by 1/2. The enthalpy of the reaction depends on the physical state of the reactants and products, so you also must specify the states. For example, here we have hydrogen gas and oxygen gas yielding liquid water, and it has a certain associated enthalpy value of negative 286 kilojoules. If we look at hydrogen gas producing and oxygen gas producing water that's not in the liquid form, but that's in the gas phase, here you see that the change in enthalpy is different. Okay, so the state of matter also is critical here. So you have to make sure you include the state of matter in your reactions, and note that if you're having to look up enthalpy values, what the state of matter happens to be. So next, we're going to look at a calculation here. We have a gummy bear that has a certain amount of sucrose. It reacts with potassium chlorate to yield a 43.7 kilojoules of heat that's produced. Write a thermochemical equation for the reaction of 1 mole of sucrose. Well, they give us a balanced equation for the reaction between sucrose and potassium chlorate. But the problem is, if you look here, it's 1 mole of sucrose to 8 moles of potassium chlorate. And we're given certain masses here that probably aren't exactly 1 mole of sucrose and 8 moles of potassium chlorate. So what we have to do first is figure out how many moles we have. All right, so the end product of this is just going to be this chemical reaction, but we also have to figure out basically the change in the enthalpy. of the reaction for 1 mole of sucrose, okay? So we can figure out what this ratio is here, and then we can do some calculations to figure out our change in our enthalpy. So let me go ahead, I'm going to move it to the Luna here so we can look at calculation done by hand. So here's our given information. We're given 2.67 grams of sucrose, 7.19 grams of potassium chlorate, and we're given an enthalpy of negative 43.7 kilojoules. It's an exothermic reaction, it's a negative value. And that's for this reaction that happened. Okay, so we need to kind of scale it up, right? But first we need to figure out how much, this is how much heat that was given off, okay, as an exothermic reaction. So we're writing a thermochemical equation for a reaction with 1 mole of sucrose. Okay, so 1 mole of sucrose. All right, so let's go ahead and figure out how many moles we have of our starting reactants here. So when I do a molar conversion here, this is my molar mass for sucrose. All right, so when I do a molar conversion from grams to moles, I get 0.00780 moles of sucrose. I do the same process for potassium chlorate. This is the molar mass for potassium chlorate. I get 0.0587 moles of potassium chlorate. All right, so I know that my chemical equation says I need an 8-to-1 ratio here. All right, so 8-to-1. So I need 8 moles of potassium chlorate for every 1 mole of sucrose. So I see that here. All right. So here when I do my ratio, do I get an 8-to-1? So do I get 8 here? And I don't. I get when I take the moles of potassium chlorate divided by the moles of sucrose, I get 7.52. So my potassium chlorate is a limiting reactant. So what I'm going to do is, since I know that my initial enthalpy for that reaction yielded negative 43.7 kilojoules, okay, and that's per 0.0587 moles of potassium chlorate. Right, when I do the math, I get 744 kilojoules per mole. So that's for every 1 mole of potassium chlorate. Okay, so if I have 8 moles, because that's what my chemical reaction is, I'm scaling up to 8 moles. My enthalpy value is going to be 5,960 kilojoules. Moles cancels, I'm left with kilojoules. So the thermochemical equation is going to be the equation that they gave me initially, plus the change in the enthalpy, which is a negative 5,960 kilojoules, which is exothermic. Why is it negative? Well, here technically this should be negative. Right? It's negative over divided by positive is a negative, so that's negative. So I basically didn't carry it through. And so here you see a negative value for the reaction. It's exothermic. And that's because heat's a product. So if we go back to the equation, you may not realize why heat is going to be a product here. Let's see. If you look back here, it said that 43.7 kilojoules of heat is produced. Okay, so when heat is a product, it's an exothermic reaction. All right, so that's what we're seeing here. Okay, so and if we, since this was a negative value, and again, they don't give it to us as a negative value, it just says 43.7 kilojoules of heat was produced. So that means it's going to be an exothermic reaction. So in general, when we're dealing with an exothermic reaction, if you have a general chemical reaction here, heat is going to be a product. I said heat was produced, so heat is a product. When it's an endothermic reaction, heat is a reactant. Okay? So heat is a reactant there. So you have to watch carefully, read carefully what they say and then kind of know what they mean by heat being produced. That means heat is a product. It's an exothermic reaction. So the value, the delta H, is negative. Okay. when they say heat was absorbed, or something along the lines of it was a reactant, or something that means that it was absorbed into the system and it wasn't a product, it was a reactant, then it's going to be an endothermic reaction. And that means your enthalpy there would be positive and not negative. Okay. All right, so let's see. Let's go back to our PowerPoint now and zoom through this. Okay. All right, so again, you have some, if you like looking at the problems on the PowerPoint, they're worked out for you there as well if you want to look at those. I like to work them out by hand so you can kind of see some of the thinking process involved in solving the problems. All right, so it's the standard state here. Enthalpy changes are typically tabulated for reactions in which both the reactants and products are at the same conditions. This is referred to as a standard state. So the standard state is a commonly accepted set of conditions used as a reference point for the determination of properties under other different conditions. So the IUPAC standard state conditions are, and this is something that you have to memorize, the pressure at the standard state is 1 bar or 1 atmosphere. Okay, 1 atmosphere is equal to 1 bar is equal to 0.987 atmospheres. The solutions are at 1 molar concentration. So the pressure of say a lab, for example, at sea level is 1 atmosphere. Okay, so in Dalton, the pressure is a little less than 1 atm. And the solution concentrations are 1 molar. All right, so that's something you have to memorize. When they refer to something being in the standard state, you have to memorize that's what they mean when we say standard state. So the standard state change in enthalpy, we symbolize that by a superscript of, it's a little 0 in the enthalpy change symbol to designate standard state conditions. All right, the usual but not technically standard temperature is 298.15 Kelvin. Okay, that's the temperature at standard state. The symbol D H with the little 0 as a superscript is used to indicate the enthalpy change for a process occurring under these conditions. Okay, and it's usually not, when it says D there, it's usually actually it's a delta. It didn't come out, but it's delta H, not. Okay. Actually, it's not, but it's a superscript 0. Okay. Instead of the subscript 0, not. Standard state can change in enthalpy. The enthalpy changes for many types of chemical and physical changes are available in the reference literature, so you can look those values up for standard state enthalpy changes. Recall delta H is an extensive property, is proportional to the amount of the substance involved. Often, change in enthalpy is normalized to a per mole basis. All right, so you notice we kind of did that. We sort of, in the previous calculation, we sort of normalized it to where we could see the energy change on a mole per mole basis. So the standard enthalpy of combustion is shown here, delta H, with the superscript 0, lower subscript C for combustion. It's the enthalpy change when exactly 1 mole of a substance burns, which combines vigorously with oxygen under standard state conditions. So this is sometimes referred to as the heat of combustion. So for example, the enthalpy of combustion of ethanol is negative 1,366.8 kilojoules per mole. This is the amount of heat produced when 1 mole of ethanol undergoes complete combustion at 25 degrees Celsius and at 1 atmosphere of pressure, yielding products also at 25 degrees C and 1 atmosphere pressure. So again, standard state conditions is temperature is 25 degrees Celsius and 1 atmosphere of pressure, or 293.15 Kelvin. Okay, so same thing. So here we have ethanol burning in the presence of oxygen to yield carbon dioxide and water. And so our should be delta here. Our change in our enthalpy at standard state conditions is negative 1,366.8 kilojoules. So it's an exothermic reaction. We know that to be true. It's a combustion reaction. It kind of makes sense that it has a negative change in enthalpy. So here is a table of standard molar enthalpies of combustion for certain elements or compounds here. So we have carbon, combustion of carbon, combustion of hydrogen, magnesium, sulfur, some hydrocarbons, methane, some alcohols, ethanol, etc. So you can see the values here of enthalpy of combustions, and that's those values are in kilojoules per mole, and it's at standard state conditions, so it's 25 degrees C, 1 atmospheric pressure. Concentrations are 1 molar if we're talking about if we're starting out with liquid. So we know the combustion of gasoline is very exothermic. Here's an example, a picture of where you can see it looks like there's some sort of fire happening there. So here's a calculation here we're gonna do. Here I'm talking about the combustion of gasoline. It's a highly exothermic process. We're going to determine the amount of heat produced by burning 1 liter of gasoline, assuming the enthalpy of combustion of gasoline is the same as that of isooctane, a common component of gasoline. The density of isooctane is 0.962 grams per mil. Okay, so here we have example 5.10, and we're starting out with 1 liter of gasoline, which is C8H18. They gave us the density to be 0.692 grams per mil. So first, we're starting out with 1 liter of gasoline, so we need to convert liters to milliliters, and then milliliters to grams because they gave us density. So here we're going to go from liters to milliliters, and then every 1 milliliter is equal to 0.692 grams. That's our density value there. So now we know the mass of our gasoline. And now we can convert mass to moles. So using molar mass. So the molar mass of C8H18 is 114 grams per mole. So here I set it up to where I convert mass of octane to moles of octane, and then I can convert moles to energy in terms of heat, in terms of kilojoules, by looking at my table here. So they said in the problem, we're going to assume, let's see, what does it say here? Assume the enthalpy of combustion of gasoline is the same as that of isooctane. So if we look back at isooctane in our table here, isooctane has an enthalpy of combustion of 5,461 kilojoules per mole. Okay, so I can use that as my conversion factor, 5,461 kilojoules per mole. So when I go back and look here, this is the conversion factor I use for isooctane, and use it and assume that it's the same as that of regular octane in octane. And so that's going to convert that to moles to kilojoules. Okay, so when I do the math here with all of this stuff, I get 33,143.2 kilojoules. So because I started out with 3 sig figs, I'm going to end up with 3 sig figs, so it's 33,100 kilojoules. The value is negative because we bring along the negative value here, because this was a negative value. So should it be exothermic? Of course it should be exothermic, because it is a combustion reaction, and of course combustion reactions give off a lot of heat. Alright, so let's see, did that one. Now here we see a figure of tiny algal organisms that can be grown in large quantities, turn into useful fuel such as biodiesel. Okay, and so here's an application of using organisms to produce hydrocarbons, okay, long chain hydrocarbons, which you can then use to burn as fuel in your vehicle. So it's really interesting how biology and chemistry come together in this instance, where you can genetically modify organisms to produce a certain type of hydrocarbon and use that hydrocarbon in order to either synthesize fuel or use it as fuel directly. So here we see a schematic where we're looking at growing algae, and then you harvest them and extract them into oil, and then you can purify the oil and transform it into jet fuel or gasoline or diesel. That's a very interesting process. All right, so here, going back to standard enthalpy values here. We're talking about standard enthalpy of formation. So we talked about standard enthalpy of combustion. Now we're talking about standard enthalpy of formation. So that is the enthalpy change for a reaction in which exactly 1 mole of pure substance is formed into its constituent free elements in their most stable states under standard state conditions. So for example, the standard enthalpy of formation of carbon dioxide is negative 393.5 kilojoules per mole. Here we have carbon and we have oxygen. All right, so pure substances that are coming together to form a compound. Okay, so which is basically the definition for standard enthalpy of formation. You have pure substances formed from its free elements. Okay, here we have free elements forming a compound here, carbon dioxide. And so the standard enthalpy of formation, which is equal to the standard enthalpy of negative 393.5 kilojoules. So by definition, the standard enthalpy of formation of an element in its most stable form is equal to 0 under standard conditions. All right, so here's the next example where we're going to write the heat of formation reaction equations for C2 or ethanol, basically, and then for calcium phosphate. All right, so we're going to try to write the heat of formation reaction for the production of ethanol and calcium phosphate. So we look here. Here we're given C2H5OH liquid, and so we're trying to write the reaction where we're basically producing 1 mole of product. Okay, and so from free elements. So here you see this compound has carbon, okay, it has hydrogen, and it has oxygen. So carbon can exist as a single atom, but hydrogen and oxygen are diatomic molecules, so they don't exist by themselves as H. Either H2 or hydrogen can be bound with something else, but as a free element it's H2, it's a diatomic molecule, so is oxygen. So next we're going to have to figure out how many we need for each. So here we have 2 carbon atoms, so I have 2 moles of carbon here. We're starting out with carbon in its free state, which is a solid, and it's graphite. Hydrogen in its free state is assuming at room temperature, so it's a gas. I need, here I have 5 plus 1, so I have 6 hydrogen atoms on the right hand side, so I need to add a 3 here to make 6 hydrogen atoms on the left hand side. And then for oxygen I have 1 oxygen atom here, and so O2, and there's 2 oxygen atoms there, so if I multiply 2 times a half, that's 1. Okay, so I basically have to manipulate the number of moles for each reactant in order to get the same number of atoms here as the product. Remember, the product can only be 1 mole of product. So here for calcium phosphate, same idea, 1 mole of calcium phosphate, so I need calcium. Okay, calcium is a free element. It's a solid, and so I need 3 atoms of it. Okay, phosphorus, I have 2 atoms there. Okay, so phosphorus actually is, it's not a diatomic molecule, but by itself it actually exists as P4. It's just something you'd have to know. And so I don't need 4 atoms of phosphorus, I only need 2. So I'm going to multiply 4 times a half to get 2 atoms of phosphorus. It's a solid at room temperature. And then oxygen, again, is a diatomic molecule. I have 4 times 2 or 8 atoms of oxygen here. And so I need 4 times 2 or 8 atoms of oxygen on the left-hand side. So that's how I would write my equations. So let's go back here to our PowerPoint. So now we're going to talk about Hess's law. So Hess's law is something we're going to be addressing in our next lab for this Wednesday. And so there are 2 ways to determine the amount of heat involved in chemical changes. Measure it experimentally, which is exactly what we did last week. Calculate it from other experimental determined enthalpy changes. And so that's what we're going to learn how to do with Hess's law. So some reactions are difficult, if not impossible, to investigate and make accurate measurements experimentally. So for those reactions, we can use Hess's law to calculate the amount of heat that's been transferred. All right, so Hess's law of a process can be written as a sum of several stepwise processes. The enthalpy change of the total process equals the sum of the enthalpy changes of the various steps. So Hess's law is valid because enthalpy is a state function. So again, doesn't matter how you get there. If you have an initial value, you have a final value, that difference there is going to be the enthalpy change, okay, no matter how you got there. So enthalpy changes depend only on where a chemical process starts and ends, not on the path it takes from start to finish. So for example, here we can think of a reaction of carbon with oxygen to form carbon dioxide as occurring either directly or by a 2-step process. So here's the direct process, carbon being turned into carbon dioxide. It has a standard enthalpy value of negative 394 kilojoules. Or in a 2-step process, here we see carbon is first converted to carbon monoxide by reacting with oxygen. And so it has a certain standard enthalpy value there. And then carbon monoxide can react again with oxygen to form carbon dioxide, and you have a standard enthalpy value there. So you can sum up these reactions here to where your net change, when you get rid of the intermediates here, your net change is going to be the same as your 1-step process. Okay, so when you all you have to do then is just add up your standard enthalpy changes. So according to Hess's law, the enthalpy change of the reaction will equal the sum of the enthalpy changes of the steps. So if I add up each step, and that should be a negative right there. I tried to change it, but couldn't because it's a picture. All right, but add these 2 values together, it gives you a negative 394 kilojoules. Okay, it should be negative. And we see here that the change in the enthalpy of the overall reaction is the same whether it occurs in 1 step or 2. So if you notice, if you remember from before, we saw that in 1 step, the standard enthalpy change was negative 394 kilojoules. When you do it, if you look at it in 2 different steps, when you add up the standard enthalpy values, it's the same value, negative 394 kilojoules. So that's Hess's law in a nutshell. You're just adding up the enthalpy values for each step instead of, because, you know, again, experimentally, sometimes you can't measure the heat change in 1 step. It might take multiple steps, and so just adding up the enthalpy values to determine the enthalpy of the reaction. So here we see a picture where we see the formation of CO2, just like we were talking about previously. And so from its elements can be thought of as occurring in two steps, which is the sum of the overall reaction described by Hess's law. The horizontal blue line represents enthalpies. For an exothermic process, the products are at lower enthalpies than the reactants. So here we see carbon and oxygen. They eventually form carbon dioxide. So you can see that there when he's releasing burning a diamond. But you also can see here when you're starting here with a diamond, and it's reacting with oxygen. You can see this small enthalpy change of negative 1.90 kilojoules. Okay, and then the rest of the heat is released in the burning of the graphite. So, you know, obviously it's easier to start with graphite than it is with a diamond, but you're going to get those values are going to be should be the same in terms of your enthalpy values. So Hess's law and enthalpy of formation, we can also use Hess's law to determine the enthalpy change for any reaction and the corresponding enthalpy of formations of the reactants and products that are available. The stepwise reactions we will consider are the decomposition of the reactants into their component elements, for which the enthalpy changes are proportional to the negative of the enthalpy of formation of the reactants, followed by recombinations of the elements to give the products with the enthalpy changes proportional to the enthalpy of formation of the products. So here we're going to look at an equation that I'm going to actually write out because it's kind of jumbled around here. In order to determine the enthalpy of formation using Hess's law. And so we'll jump over to Luna for that.